Okay, so let's start with the basics. What is machine learning? So machine learning generally is, we hear a lot about it recently. It's been around for many years, this way or another. And the idea is to write computer programs that somehow figure out how to do something without us giving it an exact algorithm of exactly a series of commands that we normally do when we write a program. So how can that happen? So it happens in several ways, and there are different kinds of machine learning that the three main ones are shown here: supervised, unsupervised, and reinforcement. And I will concentrate on supervised machine learning today because I think it's the easiest to relate to when you start. So generally speaking, think of supervised machine learning is if you have a little child that never saw elephants or mice and doesn't know what they're called. And we take this kid and we show them a picture of an elephant and tell the kid, this is an elephant. Then show a picture of a mouse and say, this is a mouse. And then show another kind of elephant, all kind of pictures of mice and elephants. And each time we show the kid the picture, we tell the kid what is the picture of. And this is supervised learning. So when we do this, the kid eventually is trained. This is the training process. And then the kid can pick up a new picture that was not shown before of an elephant or a mouse, and is expected to now figure out if it's an elephant or mouse because we showed the kid a lot of examples and told the kid what they are. So that's very similar to what we're trying to do here. So instead of writing a program that we have to say, okay, if you see a gray color and if you see this, because it's hard to tell for us. So we try to have some algorithm that just by showing examples, this algorithm will eventually figure out how to classify, in this case, new examples. And I'll go more into it in a minute. Unsupervised would be if we took a kid, the same kid maybe, or another kid that doesn't know, and we just gave them a pile of pictures that some of them were mice and some of them were elephants and didn't tell them anything. That kid will go through the pictures and eventually will figure out that there are two kinds of pictures or two kinds of animals here and can divide it into two piles. Will not know that this is called a mouse or this is called an elephant or what it does or anything about it, but we'll be able to tell that there are two distinct sets and separate them. This is what unsupervised algorithms do, usually also called clustering. They can find clusters, they can find groups and sets within the code. Reinforcement is actually more complicated, more interesting, and I will not really touch it today. It would be probably another presentation, but it's very interesting. It's when generally you don't even give any kind of feedback until a long time later. Something like if the kid is supposed to find the nicest pictures of the biggest elephants, and eventually the kid comes back with some elephants and some pictures, and you say, well, not bad, or not at all. Or then after a while of doing it back and forth, they'll start figuring out maybe what they were supposed to do. But the feedback is always not direct. Is the meaningful feedback happens eventually. So let's go back to supervised learning. This is the most, I think, basic and also most usable nowadays kind of learning. So what we have, whoa, that was a lightning and thunder. I hope you did not really hear it as loud as I did. So instead of writing a program, we have something called a model. A model is actually a program that we don't change. We don't go and rewrite the program, but it's a program that somebody already had written. It's part of a library, and it has a certain structure, and it basically does some calculation. It takes inputs, and it calculates outputs from them. And in between the input and outputs, there is a certain calculation that's being done. It's always the same, but it depends on all kind of parameters. And if these parameters change, then the output will change. Now, when these parameters are changed, this is actually called learning. And there is another program that goes and changes these parameters that control this program. And this together constitutes a model and the learning algorithm of the model. It sounds a little abstract, so here is a picture that may make it a little easier to understand. So we have a model which is sort of a black box, but it's really, think of it, for example, one example would be perhaps a decision tree that makes all kinds of decisions and branching based on the input. So these are the inputs on the left, outputs on the right. And let's say the first branch will be, if this input is bigger than 5, then go this way. And then it will come to another branch and it will say, if the other input is bigger than 10, then I'll go this way. So that tree, the branching of this tree or the thresholds that we have in a tree are all kinds of parameters that are being tuned to the problem. And the learning here is supervised. So we put certain inputs here. We know what the outputs are supposed to be because this is an example that we know. So we put in the input, we put the outputs in place, and then the model is actually generating the outputs from the inputs according to whatever parameters it has inside. And then we see that there is a difference usually. We know what we wanted. We know what the output actually is. So now we tell the model, okay, this is your error. It was supposed to be this, but it came out this. It was supposed to be this, came out this. And now the model, the learning algorithm that goes with this model is going to change those internal parameters, which are like the thresholds or whatever else that is specific to that structure inside. We'll tune it to try to make the error smaller. And then we show another example, and it will calculate the error of what it versus what it was expected to be, tune those parameters. Basically, these are numbers that it's going to change. And there is a way, each model has a certain way to change those parameters. And then this is the learning algorithm. So this will get changed and changed and changed until if the model is powerful enough, complex enough, and if the learning algorithm here is successful enough or good enough for our purpose, then eventually it will start getting the correct outputs for the inputs that we are showing it. So this was called the training process. So now we know that for the training examples that we gave it, the outputs are what we wanted. And now we stop the learning, everything stops, and these parameters don't change anymore. And the model is ready to do predictions or inference. So now we can show the model new examples, new inputs, and it will predict outputs. If we did a good job, then the outputs would be also what they're supposed to be or close enough. There could be cases where the model is too powerful, too complex, and then it basically memorized those examples. And now when we give it new examples, it will give things that don't make sense because it didn't memorize those. We want a model that is not too complicated, not too simple. That's one of the challenges of learning. So if the model was right, the model was the right size, the right complexity, we didn't train it too much, we didn't under-train it, and then it will hopefully give us correct predictions on new examples, and this is called generalization. It will be able to generate good generalization. And this is, I think this is sort of what so the process of training, also called fitting, we are trying to fit the algorithm or the model into the data that we are showing. And we're trying to minimize error. Now, error, there are all kinds of measures that we can try to minimize. There is accuracy that we can maximize accuracy. Error can be also called loss. We can have different formulas to calculate it. And sometimes you want to also look at other things like false positives, false negatives, etc., and maybe minimize those more than others. So there are many ways to measure the performance, and we usually have a particular target in mind, something that we want to minimize or maximize, and we incorporate this into the learning process. But it always comes down to we have inputs and outputs, and we try to change all kind of internal parameters of the model, and each model has different parameters and different ways that this is done. So there are two main kinds of supervised learning. One of them called classification, and this is like the pictures of elephants or mice. So the inputs usually are called features. These are all kind of numbers. In the case of a picture, it might be just the pixels of the picture, but it could be all kind of other things. We can maybe go with the picture first of the elephant and extract from it maybe the ratio between the size of the ear and the size of the nose, or the distance between the eyes versus the curvature of the tasks, or whatever else. And they're all kind of, and we just feed those features. Sometimes this is called feature engineering, trying to figure out what are the best features to feed the model. But whatever it is, the output will be what we call labels or categories. So in a mouse and elephant, it will be one of them will represent the mouse, one will represent the elephant, and there could be many other animals perhaps, and there could be a lot of labels. And when we train, we always expect one of them to be high. If it's an elephant, then we want the elephant one to go high and the other ones to be 0 or -1, or whatever the number that represents no. So it will be like a yes or a no output. And these are all kind of examples, or not yet. So these are actually examples for that exist as benchmarks. This is a very classic. This is maybe one of the oldest data sets. The idea was to recognize which species of iris out of 3 possible ones we have at hand by just looking at 4 features, which are the length and width of 2 kinds of leaves. So many times we use this as a way to validate or to demonstrate different things in supervised learning. Something a little bit newer, but by now also very, very used and very like a classic in a way, is the MNIST classification of handwritten digits. So we have a whole database, maybe 10,000, maybe 60,000, I think, examples of digits that they look like that. They're 28 by 28 pixels, which makes 784 pixels. Each one is between 0 and 15, I think. Now, 16 gray levels. So we have actually 784 inputs. And the outputs is we need to say which digit it is. So in the case of 3, the 3 is what we want. Ideally, is the 3 will be 1 and the rest of them will be 0. Let me see if there are any questions so far. Any questions? I'm looking at the comments now, so I don't see any questions, so I'll continue. These are other examples for classification that we see every day. It became really, a lot of these examples became part of our everyday life. Like the iPhone that can tell us the face, or the fingerprint. It basically does yes or no. Is it you or is it not? The other kind that is used a lot is regression. And here, the features are still features that come in just the same way. Everything is the same, but the output is a single output, and it is a continuous number. For example, classic example here are prices of houses, market value of a house. The features will be all kind of information about the house. And of course, you only see 3 here, but there are probably a lot more. There are all kind of data sets that are available publicly, and you can look at them. So there could be maybe 50 different things that go in. And what we want to come out is the market value of the house, just a number between, I don't know, maybe 0 and infinity, but some number in a certain range that is a continuous number. And other examples are, of course, the stock prices that we mentioned before, and various different maintenance windows is an interesting one that I've seen. Actually, in one conference recently, I've seen people that were trying to predict the time that it will take to upload the file. So when it tells you you have 5 seconds remaining or 10 seconds remaining, it will actually do it by learning previous examples of what happened with files that were based on this file size, the time of day, the available computing power, and things like that. instead of trying to actually calculate it, it does a better job by looking at examples and being trained on previous examples. So what kind of models are sitting? Let me go back to that picture. So we have all kinds of models, I said, in here. They were developed over the years. They do different things. They all do the same general thing, but each one of them is built very differently on the inside and has different kind of parameter tuning. But it is true that all of them have the inputs and the outputs, and they all have those parameters. So we have decision trees are very common. And there are also all kinds of models that are based on multiple trees, and random forests are such a very useful and powerful model that is built up from a lot of trees. Support vector machines are has had quite a long period that they did very well, were very popular. And my favorite is artificial neural networks that have been around for a really long time, but recently meaning maybe 10 years already, have come forward and became very useful. And actually deep learning that came out of deep learning is actually a particular case of artificial neural networks that can do incredible things and is heavily used nowadays. Any questions so far? Let me look. How do you make a balance of not overtraining or undertraining the model? That is okay. Let me go back to that more towards the end. Don't let me forget. But generally, this is really one of the main issues when you train a model. The general rule is try to find the simplest model that is still doing a good job. Anything more complicated at that point we can actually degrade your performance in the long run. But I'll get back to it later. So let's talk a little bit about artificial neural networks. So it's inspired by the actual neural networks that we have in our bodies, or not just us, but all kinds of living creatures. And interestingly, they are built of very simple units. There are just so many of them, and they are interconnected. And that's what one cell, a neuron, looks like. So on the left side, you have inputs. And the inputs are coming from other cells. There is some unit inside that sums the inputs, does something with it. So basically, this is like, in a way, this is a model. It's a very small model, but it has the inputs. It has some calculation that's done inside. It has some parameters inside. We will see it in a second. And then it has an output that is very long, and it connects to a lot of other cells just like it. So you see this part on the right side connects to these things on the left side of other ones. And the beginning of all these artificial neural networks was when we started to simulate it with a computer program, which did something like that. It would take inputs, produce an output just like that neuron, and inside try to do what actually is happening inside that cell. And what happens in there, each input has a certain weight, and then the weighted sum of all these inputs is basically is accumulated to create the sum. And then there is also some threshold or some bias. And all this is passed through some nonlinear function. The way the actual cell works, if the threshold is being exceeded, then the cell basically fires and it activates the output, and then all the other cells that it's connected to get that pulse. What we do when we emulate it using software, we don't have that firing thing. We just have a value that Y assumes, and this is a nonlinear function of that sum of weighted inputs. And that is already enough. Even that is enough to be able to make certain decisions. So a certain excess will give us a high output, and certain other excess will give us lower output. But it basically can take that input space and divide it in a linear way, which is not powerful enough for a lot of things that we want to do. But think of it that in the brain or in the neural system, there are so many of them. They're all interconnected, and this is the true power. And what we do is to somewhat emulate it in a lesser way is we do that. One common type is called the multi-layer perceptron. So each one of these cells here in these two layers do what that cell that we saw, what this neuron or perceptron is doing. So each one of them does accumulation of the weighted inputs, and then there is an output that's connected. It's the same output really that is connected to all the cells in the next layer. This is called a fully connected or dense network. But each cell is exactly like what we saw before. So now we have a lot of weights. Each of these cells have the weights, and each of these cells have the weights, and each cell also has a bias, etc. So actually, those weights and biases are the parameters that we are going to change during the learning process. And indeed, we know that in our brain, those weights, which are the strength of the connections between different neurons, and also sometimes the fact that there is a connection or there isn't a connection, or connections are being created that weren't there before, this really constitutes the processes of learning and the concept of memory. It's quite amazing to think that, but just those weights are how we actually implement learning and memorizing, just changing the strength of weights, or adding connections and adding weights that weren't there before. And this is at least what we believe, that the way that our brains work. So actually, when you start to construct those networks, they become very powerful. They can do very complex mappings from the input to the output. And there is a family of algorithms that does the parameter tuning. So basically, you put the inputs, you say what the output should be, and then you see what the error was. So you compare the actual outputs. You start with some random weights. You look at the actual outputs, and you compare them to the desired outputs, and you calculate the error, and then this error is propagated, and you use the error to somehow modify the weights here, and then you propagate it again here and modify those weights on the previous layer. This is called backpropagation. Then you keep doing it, for example by example, and eventually this is basically changing the weights and the biases this way constitutes the learning process. Now here you see what you see. So you have an input layer that doesn't really do anything other than connect. Then you have the output layer and the hidden layer, which are like those perceptrons that we saw that actually have the weights and do this calculation on the weighted sum. And actually, years ago, there wasn't much computing capability to support more than one or two hidden layers, which was still enough to do a lot of things. But nowadays, thanks to all kinds of advancements in algorithmics and in computing power, okay, I went ahead of myself a little bit. Now we have something that's called deep learning, but let's just go one back before that. Just to show us an example. So this is what we saw before, but this is one way to implement the model. So this neural network with one hidden layer, for example, can be the model that we train here by giving it those images or pixel values as inputs and telling it what the output should be. And eventually it will start recognizing digits of other samples that people have handwritten. And actually one single layer is enough to get good results, but it will be a very large one. And if you instead do two layers, two hidden layers, then you can have less neurons. And what happened over the years, the ability was achieved to put a lot of hidden layers and make the networks very, very powerful. And this is the concept of deep learning, is when you have a lot of layers. Let me see if there are any questions so far. So deep learning networks are very powerful. They can have a lot of layers in between the input and the output. The number of connections can be overwhelming, though. So, in deep learning, there were other things introduced that are called convolutional network, where you actually have some layers that they are not fully connected between the layers, but instead they do some feature extraction on the picture So you can see that generally, if you try to understand what car it is, the first layers will extract all kinds of features that are maybe edges in different directions. And then the next layer will find more complex features like wheels. And eventually, it's not necessarily the next layer, but as we go up the layers, it will become more and more sophisticated and complex, building on the simpler layers that were before. And eventually, it will come to the point that it will have the concept of car. So the concept, the abstract level of the concept goes higher and higher as we go down the network. And what you see is that the very last layers of a convolutional neural network is a dense layer, is a fully connected layer, just like the one we saw before. But this picture is also not completely representing. There could be layers like this in the middle. But there are many cases where we basically pull together a lot of detectors because we don't want to have them fully connected. It will just be too many parameters to try to control. But the deep learning network actually were able to do amazing things with images, with sounds, with video, and can also even generate videos and images and sounds that is hard to tell that were not real. And there are many frameworks. So TensorFlow is the most poorly known one, and this is what Freddie mentioned before that he was using, correct? And there are many others. And TensorFlow is based on C or C++, but there are other ways to use it from other languages. There are many Python networks, PyTorch and Theano and Keras, that are, in the case of Keras, it basically builds on, it's a nice interface to use one of the other frameworks as a backend. And there are still many others. What I'm going to show you now is actually a couple of Java networks. Java is a little bit behind traditionally when it comes to neural networks and machine learning. Python is the main, I think, mainly used language today. It is using usually libraries that were built in C for the speed. Actually, also Java libraries are leaning on C implementation deep inside. But there are a couple of Java frameworks that I can mention now. Deep Learning for J was the first, and it's the most mature. It's open source. And by the way, I'm mentioning CPUs here. Sorry, let me go back here. GPUs are graphical processing unit, and originally were created to manipulate images for gaming, to control the monitors. So they were actually video cards or coprocessors that were doing all kind of matrix manipulations, which is actually what you do to transform an image. Like take an image on the screen and flip it or move it sideways or do all kind of transformations on it. All this is done with matrix calculations, and a lot of it looks like this. Where is it? Just like this. An accumulation of a weighted sum of inputs. So it can have a lot of inputs and do like x1 times w1, x times. So those operations lend themselves very well to neural networks. So when we have a deep learning and we have so many of these operations during the learning process and also during the forecasting, people found out that GPUs are very good at it, and they use them to train the neural networks, and sometimes also to use to do the prediction after they were trained. So that's why those libraries, one of the features that they should have is the ability to be used on a GPU. So the training will take less time because they are so big, and usually, and sometimes we have thousands or tens of thousands of training, and there could be images with thousands of pixels or more. So all this can be very computationally intensive. It can take weeks sometimes, and we need a lot of power. And so GPU is usually what you do when you need to start something like that from scratch. And deep learning for J also has the ability to import models from other frameworks, and it supports all kinds of other nets. There are many kinds of neural networks that we did not cover here, and you are encouraged here to go and explore them. LSTM is one kind. I can maybe throw a few more names, but Also, I'll get to it at the end. You will get a chance to join my, or you can go to my blog and see some more of what I wrote there. You can join basically my mailing list, and we'll talk about it in a minute. So here is another library that is younger, but already does a lot of interesting stuff. It's called DJL, the Deep Java Library. It's made by Amazon, actually, by AWS people, but it's open source. And it's also for Java people. It has a lot of models built in. It has a model zoo, what they call it. So a collection of models that are already trained, and they do a lot of things, and you can just take one and use it. And this way you can save yourself a lot of work. You can just start deploying a model basically by implementing, by just taking that model and writing a small Java program that can be, for example, a REST, can have a REST interface, and then you will just send it some information. It will send you back the prediction. Also, because it's AWS backed, it lends itself, let's say, better to run on AWS as a Lambda. If you hear the barking, it's my dog afraid of the storm. It's relatively easy to deploy this Java library on a Lambda, which is function as a service, a serverless function by AWS. So let's see, I forgot, but I may have a demo. Is there a demo here? Let me try to get to this demo site if you give me a second. And I'll try to ask the dog to be quiet. So give me another second while we do that. So give me a second. Can you, I lost my place here. You guys can still hear me? Okay, so I'm going to try to go to share something else instead of what I'm sharing now. So hopefully you can see that doodle draw. Can you see that? Click twice again if you need to enlarge it. So this doodle draw, actually, let me see if I can even turn on the debug. And what this does, actually, there is a Lambda, there is an AWS Lambda, which is a function as a service. It's a serverless function that sits somewhere. And every time I doodle something, let me try something. Let me try to do this. So you can see here that it's sending this program here, this canvas on the HTML is backed by JavaScript that is sending a message, a post message to that Lambda. And in the response, it gets back a JSON object that says, well, this is a necklace maybe, and the probability for it to be a necklace is 28%, or it could be a banana, 25.9%, etc. And it will print those labels. So I can do this, and you will see those labels actually printed on a screen here. So here it just prints those labels. But you can see that basically there is a classifier sitting on that Lambda, and it takes those pixels and it's trying to figure out what it looks like. And I'm going to just, so it thinks it may, oh, now it says a chandelier. Let's see if at some point, if it will realize that it's a face. I see mouth here. Oh, smiley face is already there, but not in a very high probability. If I do another eye, will it get a better probability? Yes, so now smiley face has a much better probability. Actually, it's 46%. What if I put ears? I don't know my drawing abilities, but now it's already, let's see how. So by now it's 60% that it's a face, etc. And then I can clear it and start afresh. So this is just so this is a network that was trained that was trained and now it does predictions. Let me go back to the slides. And again, you may need to click twice on them, but to make it larger. So I'll continue. We are towards the end. One interesting thing that is happening recently. So now we can come back maybe to the question that was asked. Let me see exactly how. So the question is, how do you make a balance of not overtraining and not undertraining the model? So this is one of many problems that you would have when you go to try to build a model. The first thing you need to do really is to work. A lot of the work is done on the data of the features before they even come to the point of the model. A lot of people will tell you that this is the most important part, is how to get the best features, how to clean them, how to remove duplications, make sure that you don't have leakage from results into the input. But once you have that, you have the features and you have the data, how do you choose what model? How do you choose how powerful the model is? Because you don't want it to be, like we said before, and like the question is really asking, you don't want the model to be too powerful. So in the case of a neural network, the neural network is more powerful if you have more layers or more nodes in the layer, etc. Basically, the more parameters you have inside the network, it is more powerful. If you have a tree, maybe if you have a collection of trees, what is the size of the collection? So that's another issue that you have to deal with, and there's always a balance. You want the model to be powerful enough, but you don't. If it's too powerful, then it will overtrain itself, and it will start memorizing, and you don't want to do that. There are also how long should you train it? It's always you want to stop the training at some point before it starts memorizing. So actually, that's something I don't have here, but you can look at curves. You can see the arrow going down and going down, going down. At some point, it stops going down. That's a good place to stop training. Or you can maybe you do validation and you always test your training versus whenever you train after every round, you go and put some new pictures that was not, or new samples that were not seen before, and you test the generalization while you're training. And when you see the generalization stopping to improve, this is a good time to stop your training, even if the training itself continues to improve. So there are techniques like that, but because these are difficult questions, and you need to be an expert, sort of, or it takes an expert sometimes to figure them out. Plus, it takes a lot of trial and error regardless. There is a rise recently of AutoML frameworks that try to do this for you. So you will give it a problem, and it will try to figure out what model to use and how complex the model it should be. It can also decide sometimes what features to use, because some of the features can be misleading or noisy or not really helping, and you want to reduce them. And then you have also, you can have a combination of different models. And you have the learning parameters. There are learning parameters that are actually called hyperparameters. We didn't really talk about those, but there are parameters for each algorithm. Has parameters that don't change. You just decide what they will be in the beginning, like learning rate, or like in case of neural networks, that the size of the network is actually part of that. So these are called hyperparameters, and you need to choose them. So there are AutoML tools that exist, and there are many more that are in the making that are trying to help you do that or do some of it for you. So AWS actually called it AutoML. There is a H2O. I'm not sure if you're familiar or heard of H2O, but they have a driverless AI. That's what they call it. And then there are many more, but Teapot, I believe, is an example of a Python library that is open source. So you can just go look at that if you are Python people. And let me move to the next slide. So I'm coming now to genetic algorithms, which is really my pet peeve. This is what I like most to work with. And in the next presentation that will start a few minutes after the next hour, I will talk about genetic algorithms and several other biologically inspired algorithms. We also said that neural networks is biologically inspired, and that's another reason I like neural networks so much. But a genetic algorithm is based actually on a Darwinian evolution, the ideas of evolution. I will get to it more in that next presentation. But it's a way to search for the best solution in problems that are usually very difficult for other methods to find the best solutions because the problems are too big, or there is no way to mathematically analyze it, or there are all kinds of traps where another algorithm can get stuck, think that it found the best solution, but it's not. So genetic algorithms actually are used in many cases in AutoML because it can look into all the combinations of features and types of models and different values for the hyperparameters and combinations, etc., and eventually find the best combination or really good combination in somewhat of a reasonable amount of time. And therefore, genetic algorithms now also see rise. Even though genetic algorithms exist since the 70s, they were maybe used more since the 80s when they were more popularized, but now, again, they see even a newer interest because we can use them to help machine learning and improve models and to find the best combinations that will give us the best models. And I will talk a little bit more about genetic algorithms in the next presentation. And I have written a book, which is mentioned here. And the book is talking about genetic algorithms in general, how you solve all kinds of problems with it of different types. And then towards the middle of the book, chapter 7 and on, actually, it talks about applications of genetic algorithms when it comes to machine learning. And that chapter 7, which also includes some introduction to machine learning and shows you Python programs where you do the machine learning and then you improve those models with genetic algorithms in certain ways. This chapter you can download for free in this link, or this if you take a picture of this, or if you go to the booth. There is a booth, there is an expo in this. If you didn't know, I'll mention this in any case. There is an expo area of this event, and you can see it on the left side. You can maybe open it on with the right click and open it in another tab. And that expo actually has a lot of offerings from a lot of the speakers and presenters here, and you can get a free chapter or a free book or different things from those booths in the expo. In my case, when you go there and download the free chapter, or it will basically send you an email with a download, and it will also put you on my mailing list that goes with my blog that is called AI for Java. So as you see, I started, I'm more of a Java person, and I started my blogging about Java, but then I went and wrote a book that was about Python. So that blog will not be limited just to Java. It will be programming. It's mainly, the way I see it now, is AI for developers. So if you join that mailing list, it will start sending you the existing blogs that are a few at this point, and then as I make new ones, it will keep sending them to you. So you can also opt out at any point. So this has been that first presentation. We have a few minutes if you want to ask questions, or if anybody actually wants, again, to join me in the video and say anything or ask anything in person. Let's do that, and I will return my picture and remove the screen. Let me remove this. Okay, so any question? Okay, so I see that, yeah, a lot of people here cannot resist Python. Yeah, Python makes things very, very, I don't want to say easy, but very pleasant and flowing. And you don't have to waste time on things that you don't want to deal with when you use Python. You will find that somebody has done that part already, and you can concentrate on the stuff that you want to deal with. So Python does make definitely a great way to do machine learning. However, I have to say that Java is trying to fight now. Java is trying to put up a fight. There is also a Java, let me put it in the. Actually, I put the other link there too. Where is it? Give me a second. So first link here is the demo site that I did with the DJL. This is that link. I think it's also in the presentation itself. And let's see if I can find the one that, so here is the VisRec visual recognition API that was created for Java. And that is the first sign of making machine learning part of the language itself or part of the APIs that the Java offers. And I believe that Java is about to come up with all kinds of other ways to do machine learning in ways that are supposed to give a good fight to Python, to basically to enable Java developers to quickly create all kinds of machine learning applications. And that's a great thing, because if Java does get as good as Python, and Python may try to fight back again and get even better, so that can only be good for all developers. So I can finish here unless you have any other questions. If anybody again wants to, and I'm basically going to stay now and start the next presentation a few minutes after the hour. So meanwhile, if anybody wants to ask anything, anybody wants to come up on the video and talk to me with a picture, with a video on, or to anybody else, I welcome you to join me. Do you guys prefer that I just take a break and come back in a few minutes, or would you like me? Or otherwise, I'll just stay here and wait for your questions, or for you to join me in person. Oh, there is somebody there. I'm sorry. Are you still there? Ram? I missed you. I don't know how long you were waiting there. So let's see if Ram is going to join me now. Okay, thank you, Stephen. Thank you, everybody, for being here. And again, I don't know if Ram is still around, but it looks like he was trying to join me, and I actually didn't see that. So Ram, are you still there? Give me a shout on the. Yes, I can share the slides, but I don't have them. I can't give you a link right now because I don't have them online. So that's something I didn't think about. How about let me try to put them online somewhere tonight, and I will send a message through the event. I'm not sure. I have to talk to Bruno. My handle is this, and I can give my LinkedIn as well if I can find it myself. I'm waiting on LinkedIn. And here it is. So this is my LinkedIn. You can see, by the way, that I personalize it, and it's called Eyal AI. If you want to personalize your own LinkedIn profile, you can just Google it, and you can find there is a way to do that. If no one else did the same thing before you, it's actually very easy to do. So I should have been able to remember that, but I still had to go look for it. So I will find a way to share the slides. I apologize for not thinking about it in advance. Through the event or through the emails from Bruno. There is a question. Oh, I see. I'm sorry, I missed that. What is the difference between machine learning and data science? I think data science, machine learning is more well-defined, perhaps. Data science is a combination of different things, or at least that's what is common to think. That data science, I think, is at least a combination of three things: of math, computer science, and the domain expertise. That's at least one presentation I saw. That means that when you go to solve a problem, you need to understand that the domain of the problem to some degree. And then you need to be able to figure out the math behind it, the statistics, and be able to gather information and clean the information, and then basically implement it as a program. So the machine learning really is more of the software part of it, where it helps machine learning also to understand the aspects of the statistics, etc. But data scientists will also deal with the data, a lot of data cleaning. Let me just turn this off. There is the aspect of data cleaning, data preparation, deciding what features to use, where to collect the data, making sure that things make sense. So data science has a lot more aspects than just machine learning. And in many cases, data science is done in a team. It's true that you have people that are called data scientists, but if you know several data scientists, you might see that they are not all doing exactly the same thing. They don't have the same background necessarily. Some people would be software developers that turn into data scientists. Some of them could be mathematicians or statisticians that turn into data scientists. And some of them could be just domain experts that came from a certain domain and became data scientists there. If you see a place that specializes in machine learning and artificial intelligence, they will usually have teams working, and there will be different specialties within the team. Even if they're all called data scientists, they will actually could have different aspects of specialty. But I know that there are also programs in university where you graduate as a data scientist, so I would think that they try to put into that all kind of combination of computer science, math, and machine learning as a thing by itself. I hope that answers the question to some degree. There is also something called machine learning engineer, by the way. Machine learning engineer, I think that varies a little bit too. In some cases, machine learning engineer will not necessarily deal with the data science part, meaning the data engineer is not going to decide what the model is or how to train it, but instead will be dealing with productizing it, taking the model and turning it into an actually software that's running, that's deployable, that you can actually serve from a server, get requests, respond to them, make sure that it's scalable, that it's maintainable, that it's up and running. There are also aspects of monitoring. When you have a model running in production, you want to know that it's still doing a good job. Even by the time it was trained, it did well. But maybe over time, things shift. The data is not, you can sometimes sense that the data coming in has different characteristics than the original data because of trends or because of seasons or whatever else. And you need to monitor that and make sure that your model is still working correctly. And so you have a very interesting CI/CD or a DevOps aspect for machine learning software. And this is usually dealt with by machine learning engineers, who again are not necessarily data scientists, but they're very good. They understand machine learning and they're very good at making it a working product. So I'm open for more questions if anybody has in a few more minutes. Let's say 10 minutes after the hour, I will start the next presentation. So I will go for a second just to my PowerPoint and make sure that other presentation is there. Okay. So it's there. No, he's Scott. What about someone who knows nothing? Where should I start? Well, you should have started in the beginning of my previous presentation. Were you there? I was talking about what machine learning is and how it can be used. And if you missed that, then my blog, it's okay, I'm just giving you a hard time. So you can join my, one way, I mean, there are many others, but I do have a blog that's called AI for Java. And when you join the mailing list of the blog, you will get some of you will get the existing blogs, the posts that I wrote, and they start at the beginning, like what I did today, maybe a little bit more in detail. What is machine learning? What you can do with it? What are models, and etc. And again, if you download the chapter for my book, by going to the expo, if you go to the expo, you will see my book there, Genetic Algorithms book, but that chapter that you download is also an introduction to machine learning, because it's the first chapter where I apply genetic algorithms to machine learning. And also that would put you on that same mailing list of the AI for Java blog. But there are many resources. There are also real classes. There is a machine learning class by Andrew Ng, right? I probably, well, actually, one of the people here asked me before that, like a few days ago, about what could be good resources. I can go to the answer I gave him and copy some of the links and put them right here. Give me a second and I'll do that. I'm going to turn off my camera. So here is one link. It's not necessarily the first link, but Kaggle is the website that's all about data science and machine learning, and they do have their own learning. They offer some free classes and training about machine learning, and they start from the very beginning. Let me get the next one. Oops. And this is the class I was talking about. This is the classic class about machine learning that you can take for free. You join it. It's like Coursera, but it's actually a university class, taken by many people. And one other one is Amazon. So Amazon AWS has a lot of machine learning in the cloud. That's true also for Azure and Google and Oracle. They all have a lot of machine learning capabilities that are built in, and you can either use them as a service, just sort of like the Doodle that we did before, which was a service that's out there. And but Amazon also has free training that you can take. Some of it is free, some of it is not. But you should basically open a free account with Amazon for a year, and you mostly don't pay. And you can do that training will walk you through building from AWS building blocks and experimenting, which is the best way to learn anything, and of course AI as well. And oh, I see more from Scott. Will your book get me started? Where is the best place to buy it? Okay. The book will actually get you started in machine learning once you hit chapter 7, which is the chapter that you can download. The book is actually about genetic algorithms, which is also a part of AI, but genetic algorithms are not limited to machine learning. Genetic algorithms are a very powerful tool to solve all kinds of problems. So the first 3 chapters are just how you get started with genetic algorithms, understanding the concepts, and chapter 3 is actually about a particular library, a Python library called Deep. And then chapter 4 and 5 and 6, you can see how to solve different kinds of problems that are not machine learning, but are very useful problems that you can encounter in everyday life and in all kinds of situations. And I will actually talk about it very soon. I will start in a minute. And then when you hit chapter 7, you will start seeing how you apply genetic algorithms to machine learning. So it actually gives you an introduction to machine learning. And it will do things like a feature selection and hyperparameter tuning, and how to select the architecture of a neural network. And you can see how genetic algorithms can be used for these things. And later on, it will go more into image processing, and at the very end, it will talk about biologically inspired algorithms beyond genetic algorithms. So this is exactly bringing me to the next presentation. So I'll get started with that. Let me share screen. Okay, can you guys see that? Please double click the slides so to enlarge them. And I will go dark and start talking. So this is sort of a topic that is not spoken a lot about, but it relates to artificial intelligence as well and problem solving in general. And there are many algorithms, and they've been around for a long time, but there is a renewed interest in them nowadays. And they are inspired by biological systems or behaviors, because nature has a way to solve problems. Nature, especially living organisms, are solving problems all the time, and if they don't, they disappear. And the ones who do solve the problems are the ones that remain. So we can learn from this vast experience of what's happening around us, how different problems were solved. We can look into that and perhaps make some shortcuts and use that information instead of trying to solve everything from scratch. So actually, the main thing, okay, let me just show you, I guess I chose here in the beginning of the presentation just to show you a problem that maybe we want to solve one day. But that's a problem that has been discussed for generations. It's called the traveling salesman problem. What you have here is actually, let me see. Okay, I thought I maybe had here a map that shows it, but I don't. Imagine this is a map, and these are cities on a map, and it's actually true. These are cities in Germany, I believe. There are 29 cities here, and you show you the location on a map. The original problem said you have a traveling salesman. He's going to go to all those cities to sell his stuff, and to make it the most economical, we want to find the path that is the shortest. He needs to visit all those cities, and each city can only go once, not go back to the same city twice. And we need to find the shortest route here. Nowadays, it's just as relevant. Think of the Amazon truck going to deliver packages, maybe not to many cities, but maybe these are houses in a neighborhood or some part of town. And you want to design the route for the car, to the truck, to go through all these places and drop the packages. And here the distances might be different, not necessarily distances on the map, but it may be the driving distance or how much gas it takes. You want to find the fastest way or the cheapest way, the most economical way to visit all these things. The same thing with the drone. That will be soon, instead of a truck, or in combination with a truck and the drone will have to fly maybe. And a drone is very limited. Maybe a drone can only fly half an hour or an hour at a time before charging or replacing batteries. So this problem can be actually expanded and say, what if you have now several drones or several cars and they all come out of somewhere in the middle, and what's the best way to divide this between them? If you just go to the regular traveling salesman or salesperson problem, you can actually calculate there are many, many, many possibilities, as you see at the bottom. I don't even know how to say this number, but it's obvious that you can't just try them all and figure out and just find the best by trying them all. You have to find some better way. And there are all kinds of algorithms to do that. But the algorithms I'm going to talk about today this is one problem that they can deal with. One of many, but this is a classic problem that you use it as a benchmark or just to see that proof of concept, etc. So in this case, this is the solution. This is the shortest route. And in my book, and also you can see my code is in GitHub for the book. If you know the name of the book, you can find the GitHub. And there are also videos there that show you all these programs running. So I was too lazy to show you now, but I have a program that will basically do that. And all kind of other things. So here is the other problem. Here we took just the same points, but we selected this point that was sort of, and we say, what if you have 6 different vehicles, and each one of them has to start here in the middle and come back to the middle? What is the best way to divide it between them? So here the criteria was that you want to basically divide it equally between them. So you look at the shortest route here, or the longest route here, and you want to minimize the longest route. So that otherwise it might decide that one car will do everything, and it might be actually shorter than having 6 cars, but it will take longer in general. So anyways, this is just another problem that you can solve it easily. Let's say it's not a big deal to do it with the algorithms that we'll see today. So let's talk about genetic algorithms. The genetic algorithms are the most prominent of these algorithms because they're like a Swiss Army knife. You can solve all kinds of problems with it. These problems are just one type. They're actually combinatorial problems because we have a list of cities, let's say 1, 2, 3, 4, 5, and you just want to find the correct order. So you have all kinds of permutations. You can do 1, 2, 3, 3, 2, 1, 2, 3, 4, 1, etc. But there are many other kinds of problems you can do with genetic algorithms. So genetic algorithms generally talk about Darwinian evolution that I mentioned before. So how does Darwinian evolution work? Well, let's see how genetic algorithms work. And they're more generally called evolutionary computation because there are some other algorithms that are variations of genetic algorithms, but they all work in the same principles. And the idea is sort of try to imitate the idea of Darwin, not necessarily exactly what happens in nature, but the ideas. So what we do is instead of having one solution at hand and try to do things with it, we take a population of solutions, and they are not necessarily good solutions. We start by random. So in the case of that list of cities, we will say, okay, 1, 2, 3, 4, 5, 6, and then another one will be 7, 8, 2, 3, 1. All of them will have all the cities, but they will be random. So naturally, like in nature, the individuals are all the same population. They're sort of alike, but each one of them is somewhat different. So we find the ones that are better. We go and evaluate them one by one, and we see, okay, this solution gave us this distance. We want to minimize the distance, right? So we test them one by one, and we can rank them. We can say this was the best solution, gave us the shortest distance. This one was a really bad one, etc. And what we try to do now is apply what we call genetic operators. They're called selection, mutation, and crossover. So basically what we do is we try to take the better solutions, and the order here is not the real order. So selection is the first thing, and then crossover will be the second one. So in the case of genetic algorithm, we will try to take the better solutions and do a crossover. Crossover is two solutions and making offspring out of them. Usually we'll take two solutions, somehow mix them together and create two new ones that are called offspring. And to do that, we will see later how you can take two solutions and make two solutions out of them. But the idea is using genetics. You represent them with genetic material, and then you can take this genetic material and just mix it and create two new solutions. That's why it's called genetic algorithms. And then you can also go and do mutations. You can take the genetic materials and just change here and there a little bit and create some potentially weird but maybe good ones. And what happens if so you take this population, you do all this, and you end up with a new population of all the offspring, and you forget about the parents. You now have the offspring that replace them, and you keep doing it. And every time you get a new generation, because every time you select the better solutions and you use them to make the next generation, then the generation generally get better and better, and they are more adapted to the problem. So over time, you will get some good solutions in the population. And then when you decide that you had enough, you can just take the best solution you have, and this will be the solution that you end up with. And this actually works, as far-fetched it may sound or not, because it also makes a lot of sense that it should work, because that's how it happens also in nature in a way, or at least that's how we perceive it. So this is just a representation, a graphical representation of it. So we start with some random population, and then you do evolution, or something that we think of as evolution. And at the end, we take the best solution, or several of them. And the way the main loop inside goes, we evaluate all the solutions. So in the beginning, they're random, but some of them will be better than others. Then we select the better. Now, we don't just select the best one always. We just give them advantage. So we can select them randomly, but we will give advantage to the better ones, so they will have more effect. And when we select them, they are selected basically to be the parents of the next generation. And then we take those parents and we somehow mix their genetic material to create the next generation. And then we can also do some mutations on those offspring. And now we got a new generation. We do this again. And we just keep doing it until we decide that it's been enough generations, or we found a solution good enough, or we ran out of processing time, or whatever it is. And to make all this possible, like I mentioned, you need to represent every solution with genetic material that we call a chromosome, for example. So the easiest to understand kind of chromosome is like a binary chromosome. If we could represent a solution like that, then we would use that. And there are some problems where this will be a good representation. For example, if certain things we decide if we want them or not, like there is a problem that says, let's pack items in a bag, but we can't have more than the bag. The bag is limited, so each item has a certain volume that it occupies, a certain value, and we try to shove as many as we can to get the best value, but we can't have them all. So we need to find a combination of the ones that will give us the best value. So here, each item can have a 0 or 1 that will say, are we packing it, are we not packing it? And then each solution will be that. If we had 9 items, in this case, each solution will say, okay, we don't take this first item, we take the second item, etc. Now, in the case of those, the traveling salesmen, where we have to say that the cities have to be visited in a certain order, the chromosome will look more like that. It will have a series of the indexes of the cities. So if we have 5 cities, this is a possible chromosome. And another chromosome will have the same digits, but in a different order. And also we can have floating point, because some problems are just floating point inputs, like the weights of a neural network, right? The weights are floating point numbers. If you wanted to find the best weights, this was something we mentioned in the previous presentation. So, but if we have a problem where the solution is made up of floating point numbers, then we can just have a series of those numbers. So when we have this genetic representation, we need a way to evaluate it. So if we had that, for example, that problem where we can pack certain items and certain items we don't pack, then we have to evaluate and see, okay, so these items, the value of these items was so and so, and this is the value that we got out of them. And also we need to make sure that we don't exceed the capacity, which can maybe disqualify the solution altogether. In the case of the cities, which is more relevant to us, so if we had something like this, we will evaluate it by saying, okay, let's go to this city and then to this city. So what was the distance? And then the distance here, and we sum the distances, and this is the evaluation. And then we say, okay, so the distance was so and so. If it's a shorter distance than others, then it's a good solution. If it's a long distance, then it's not such a great solution, etc. And now we come to those genetic operators. So selection is where we take the better solutions. And there are all kinds of ways to do this. So it's random, but we give better probability to select the better individuals that have better fitness. I'm not showing you how it's done, but there are all kinds of ways to do it. Just we won't have enough time to describe all of this. The crossover is how we, so here's crossover. So again, it's easier to show it with the binary chromosomes, but in binary chromosomes, it's very easy. One easy way to do it is called a single point crossover. So we just cut them and we swap them around. So if these were the parents, now these are the offspring. And you don't see it here, but if we had, in the case of the cities, where this would be like 1, 2, 3, 4, 5, and this will be 2, 3, 5, 1, we can't really do this exactly like that, because then we can have the same number twice, and we will not have another number. We always have to have all the numbers, so there are other ways to achieve that. which you'll have to read about it either in my book or elsewhere, but there are all kinds of ways to achieve that, to preserve the fact that we have only one of each number. In the case of floating numbers, also we have ways to do that. And you can come up with your own ways. That's part of the genetic algorithms let you be very creative, because you can decide how the chromosome looks like, how you make the mating of chromosomes, and how you make mutation, which is the next thing. So in the case of binary, it's very easy. You can just you can choose a bit by random and just flip it. Or you can do other things. You can take this half and switch it around with the other half. There are many standard ways of doing things, but you can also come up with your own way. So the advantages are something called global optimization. A lot of algorithms get stuck in the local optimum. Basically, they think they got to the best place because everything around it, they try to change a little bit, they see that it gets worse. So they said, I must have found the best solution because everywhere else around me is worse, but sometimes the best solution actually is far away in another place. Genetic algorithms are not going to, are more immune to that because they jump around all over the place and they have a large population. And you don't really need any mathematical representation because you just have to be able to evaluate the solution. And there are some other things. I think I should be maybe moving along more quickly, so I will not go over all of this. One interesting thing is that there is an ongoing, it can be used for ongoing improvement because the evolution doesn't have to stop. Once you got a good solution, you can keep doing it though. And if the problem starts to shift and starts to change, then the solution will shift along with it, and you will find the best solution. So if you keep doing it all the time, you will always have the good solution for the time of the problem, for the current problem. So here are all kinds of problems you could solve with it. Things, combinatorial things like the traveling salesman, the routing of vehicles. Then there are problems of scheduling. If you want to schedule your workers in shifts, and you have all kinds of constraints. You can have the same worker or nurse, for example, doing 2 shifts, one after the other. You have to put a break in between. Or you can have the same person be in 2 places. So these are constraint problems. If you want to schedule jobs in a machine shop and there is just one machine that does certain things and you want to take advantage of it as much as you can, but there is a certain process that you have to follow. Before something gets to that machine, it has to go to another machine. So you have all kind of constraints there. Think of also a schedule of classes, even a schedule of a conference, like we have here. If we have a lot of people and not enough room, a smaller number of rooms, etc., then there should be some. It's a problem that you need to solve, how to schedule everybody and be able to fit within a certain number of rooms, and how to make the timetables for everybody. It can also use in design. Let's say that you have a bridge and you want to find the best way, the best shape, the best combination of structures to make the strongest, lightest, cheapest bridge, etc. Antennas is another way. You want to maximize certain properties of the antenna, and you have many, many possibilities that you can choose from. And then finally, machine learning, which is the most interesting to me, and half of my book is about that. So things that we mentioned also in the previous presentation, to make if you have a machine learning model and you want to improve it, there are things that you can do. You can, perhaps not all your features are needed, or some of them are maybe interfering and they're noisy. So you have all kinds of combinations of features. So you can maybe eliminate some of the features that are coming into the model and maybe improve the results. And you can see in the book that there are cases where you can see that you eliminate most of the features and you actually get better performance. Hyperparameter tuning, and that also, we mentioned that before. Each model actually has hyperparameters that control the way the learning will be done, like a learning rate, splits in the tree, etc. And you can get very different results. The learning will lead to different results if you set the hyperparameter a certain way. And there are all kinds of ways to find the best hyperparameters. Genetic algorithm is one good way to do that. And then we have the neural networks that we saw in the previous presentation, and they can have different architecture. They can have different number of layers, different number of nodes in a layer, maybe places where we prune the connections and we just eliminate the connections and we can make there are a lot of decisions to be made there, and genetic algorithm can help there. Also in other things like choosing the model to begin with, choosing a combination of models to work together. And again, as I said in the previous presentation, now it is used in some tools that do AutoML, tools that are becoming now prominent in the market, and try to make the decision for you or help you make the decision about what model to use and what parameters, what hyperparameters to use, what features, what to do with the features. Some of it is also feature engineering. You take several features and you try to make new features from them. So one of the technologies that those AutoML tools are using is genetic algorithms. It's not the only tool. They can use other things as well. Oops. So that would be it for genetic algorithms. And as I said, my book, most of my book is about genetic algorithms. And in the last chapter, I go into other algorithms that I'm going to try to cover now, to some lesser degree than genetic algorithms, but I think they're also very fascinating. The first of them is called genetic programming. It's actually an extension or a special case of the genetic algorithm. Basically, what we say here, we were trying to find all kinds of solutions that will be like the number of cities or the schedule or the routes of the cars, etc. But what if the solutions that we're looking for are actually a computer program? Let's try to generate a computer program that will do something that we need done. And by saying computer program, it's not what you would envision, perhaps. It will be sort of a messy program because it will be generated automatically. And usually it will be more like a function or a very complex calculation. But let's say that we have certain inputs. We want to get the outputs that we want. We want to write some function that does that. Let's try to have a genetic way to create that program that will do that. So to do that, we usually use a tree structure for the gene, for the chromosome. So before that, we had a chromosome that was linear. We had like numbers in a row, like zeros and ones, or floating numbers, or just integers. But now we want to represent the calculation, or what the program does is a tree. So what you see here is a tree representation of the calculation at the bottom. So there will be x divided by 11, and then 2.2 minus that. And then all this is added to cosine of y, and then multiplied by 7. So this is what this tree represents, this calculation. So if we have a chromosome that looks like a tree, how do we do a mutation or a crossover? So this is a sort of a visualization of a crossover. So in crossover, we basically these are the parents on top. So to cross them over, we take a piece of a tree from each one of them, and we swap it. So this part got here, and this part got here. So now we have two new programs or two new functions or calculations here. Sometimes it invalidates. We have some cases where, oops, what did I do? I don't know. Went back. So sometimes we have to make sure that we don't invalidate the program, that the program is still correct. It's easier to do with languages that have an internal representation of a tree. Python is actually one of them. So it's relatively easy to go from this representation to evaluation of the program to actually running it. But there are actually books. There is a guy called John Koza who wrote many books with many examples where he solved a lot of problems using that. And I think he used Lisp, not necessarily Python. But by the way, in the book I talk about a particular Python framework that is called Deep. Now I'll write it here. There are many others, but if you just go and look for Python Deep, if you Google for that, you'll find it. So that framework has genetic algorithms, but it also supports genetic programming and a few more that I'm going to mention, that some of them are covered there. And In my book, I actually solve an issue. I do a genetic programming example where I try to find what we call a parity problem. But I don't have time to mention it now. So let's go to the next thing. I'm not sure why this is here. I'll come back to this later. The next interesting algorithm is called the ant colony optimization. So this is not genetic anymore. It's just an observation of how ants locate food. So not all ants, but certain species of ants. So they come out of their colony and they are going to look for food. And this is also a sort of a communication mechanism. So what they do is they go randomly around, and if any of them finds food, it goes back, it takes some of it, but it goes back to the colony, and along the way, it deposits pheromones that other ants can sense. Interestingly, the pheromones don't remain, they start strong, but they evaporate over time. But when other ants sense the pheromones, they follow that, and they do the same thing. And they deposit their own pheromones. If there is still food left there, when on the way back, they deposit more pheromones. So what happens is that after a while of doing this, the shorter routes that have more food will have more, they will smell stronger because they will have more pheromones there. If it is a longer route, then the pheromones will evaporate more before the ants come back. And also, if there is less food, then there will be less ants doing it. And eventually, there is a sort of an effect of positive feedback and negative feedback. So the shortest and most abundant sources of food, the nearest resources basically will get more and more pheromones deposited, and the ants eventually will just keep going there. And this way, they basically tell each other where to go, and they will find the closest. So this is really a solution for an optimization problem. You want to find the shortest route to the most food, and that's how they do it. So there are algorithms that take advantage of it mathematically. So this is just a visualization. I could have had it before on the screen. So you see that there is, here it's a very simple case. You have food and you have the colony, and you just want to find the shortest route. So after a while, all the ants will follow the shortest route because maybe a couple of them not, but the pheromones will be a lot stronger on the shortest route. There actually, if you look on YouTube, you will find simulations of some people did with a bunch of ants and a bunch of sources of food. And you'll see that at first, the ants go in random, they scatter all over the place, but over time, when they start finding the food, you will see that the ants basically follow, they all go to the nearest sources of food. And when they finish with them, then they will find the next closest source of food. And that's another representation. You have different ways to get there, but eventually the one that will be traveled the most will be the shortest route. So of course, that immediately it could make you think of this problem that we saw before, the traveling salesman problem. So there is a very nice way to solve it with the ant colony optimization algorithm. But basically, you start by finding random routes, and then the routes that are better get better pheromone or simulation of pheromone. And then it means that more ants will follow those segments that were part of that shorter route. And over time, you will find the best route when you do that. And you can look it up and find all kinds of simulations and demonstrations of that. Let's move to the next one, maybe the last one for today. It's called the particle swarm optimization. It actually comes from swarms. I should have had a nice picture of a swarm here, but you can think of a flock of birds or a school of fish. And they seem to be moving in unison, even though they are not, they almost look like one being, even though they all have their own minds. And they do this by following certain rules. I don't think we know everything about how they do that, how they know certain things, but we can imitate it using very simple rules. But the idea is that they all rely on feedback from each other and their own, and also their own knowledge, and that make them all work together and achieve a common goal. And the way we do it in the particle swarm optimization is that we start with many solutions. We have a problem that we want to optimize. We want to find the best solution. So we have each particle is actually a solution, or it stands in a place that is represents a solution, but it moves around. And there are certain rules that tells the particle how to move. So part of the movement is based on the memory of that particle, where it was before and where it is now, and where if it was better before or it's better now, and it moves somewhat in the direction of what it thinks it's better. But other parts of the movement are dictated by what everybody else found, and where is the best that everybody else was able to find. And maybe the best way to see it is if I show you this, but let's just, so maybe I'll go to this and then go back. So if this is a particle, each particle has 3 different forces. The inertia is basically what it was just going, the direction it was going from the previous step. The social force is according to what it knows is the best direction that everybody else found. And the cognitive force is based on the best place that this particle found. So here is the definition of it. And it's basically what we see, what is arrows, the arrows in the picture denote is a directional speed, or let's call it velocity. So this is a bigger velocity in this direction, a little smaller here, a little bigger here. And when you combine them together, so this is how you combine them. You may remember doing it in physics in high school, that you combine vectors together. So you combine this plus this plus this, and then the sum of them actually is the green arrow, and this is what it's going to do. So at that point in time, when it has all these 3 forces, it will actually continue now in this direction. And when you apply this to everybody, in each round, you calculate the new velocity of every one of the particles, and then you will evaluate the solution, so it will know if it's the best that it found so far or not, or where it is now. And you keep doing it, and you see, you actually can visualize it. Hopefully you can see the visualization here. Then it's sort of cool. So at the beginning, so now we are sort of at the end. Let's wait until it goes back to the beginning. But those X's are solutions, so it started over. And you can see these yellow arrows that show you where they're going to. The interesting thing is they never really stop. They always keep moving around. But at the beginning, they very quickly converge towards the better solution, which is here in the middle. It actually, here they're looking for, let's say, the lowest place on the function. There are many other lowest places along. There are other sort of traps here around, but the best place is in the middle. So some of them actually get trapped a little bit, as you can see. But generally speaking, they sort of zero in into the direction of where the solution is, and then they hover around it and they keep moving about. But they basically, if you now take the best solution you have among them, it's the best solution that you could have in general. So this is sort of fascinating. There are also other demos that I couldn't use here because they were not royalty free, or they were not uncopyrighted. But you can find them. It's quite fascinating. Yeah, I agree. I was looking for something like that, so I'm glad I found one that I could actually use. So these were pretty much the ones I wanted to cover, but there are a few more. Oh, also there are something called robotic swarms. It also sounds fascinating. It's actually not the same kind of swarm algorithms, but it's just the idea here is the idea of collective problem solving or collective intelligence. You have just a group of robots, or it could be any other program, but the idea is they're all similar. They all can do the same thing, but they can learn to divide. If there is a task, they can learn to divide it between them and together work on a solution. And that's another branch. It's fascinating by itself. And here are a few more. Neural networks that we mentioned before are actually biologically inspired. We mentioned it in the previous presentation, and it's used for models for machine learning, because this is how we believe that our brain learns and memorizes. Artificial immune systems are very interesting because you can use them for, as an example, you can use them for virus protection, for software. They can be used to learn how to detect new threats that weren't known before and how to immune themselves against it next time they see it, they will respond a lot harder. And there are all kind of interesting ways that this is done. Artificial life is more of a general thing, just like those swarm of robots. It's trying to create programs or machines that imitate certain aspects of living creatures. Sensor networks are also based on what we have in the body, but they can be used in IoT, for example. Learning classifier system is some kind of a combination of genetic algorithms and machine learning models. And there are many more. If you look it up in Wikipedia, anywhere else, you can see all kind of interesting wolf packs and honeybees and all kind of things that we can learn from nature and were attempted in all kind of ways and variations. And I guess my book was left behind here. We saw it somewhere here. So again, this brings me to my book towards the end, which talks mostly about genetic algorithms, but at the very last chapter talks about and demonstrate a couple of the things that we mentioned here. If I was to write another book, which I'm probably not going to do anytime soon, I would try probably to write about biological inspired algorithms in general and try to increase on the scope of the genetic algorithms. And again, I'll go to the end here. So that book has the free chapter that you can either follow this link here or that QR, or you can go to the expo. On the left bar, you have the expo. You can go to the booth that has that book, and it will also get you to join my my mailing list, my blog. Okay, I'm going to turn on my camera, unfortunately for you. Yes, I see a question here. Can we use artificial immune system for curing corona? Possibly, but I guess it didn't happen so far. The artificial immune system is more to do software tasks, is to protect against threats, security threats. But there are all kind of things that there are all kind of ways, because there's so much data available, and a lot of what we do today is data-driven. Then I presume that a lot of the machine learning in general and those algorithms here could have been utilized to fight corona in all kind of ways. I'm not sure if you can actually go and find a vaccine for it, because I'm not sure exactly how they make the vaccines. Now, if the vaccines are made by trying to find all kind of combinations of materials together, and they have a way to simulate. So, for example, you have maybe you can say, what happened if I take this and this and this, put them together somehow? How is that going to fight corona? If you have a way to simulate it, then genetic algorithms can solve a problem, because it will try all these combinations from you and very quickly evolve into good combinations that are potentially what you're looking for, instead of you going and trying all this by random. Genetic algorithms will be very good at finding the best combination that you can have. So if you know that you have certain materials that some combination of them could fight corona, and if you have a way to test it out in simulation, I don't think you can just go and do it on people, but if you have a way to simulate it, then definitely genetic algorithm is something I would use. I don't know if that is the case or not. Oh, here's Jyoti. How are you doing? What are the other books and references? That's a good question. There are many books about machine learning, and I recommended a few links about machine learning. It's actually up there, not too far above. These are machine learning. When we come to biologically inspired algorithms, I am not sure there is actually a book that covers them. There is a lot of material all over the internet, and also scholarly papers and articles. But I can't think of. I haven't seen, or maybe I haven't really looked for, but I haven't seen any book. And so I tend to believe that there is no one book that covers bio-inspired algorithms. However, there are books that talk about the very first books that came that had to do with genetic algorithms. There is one book of Holland from the 70s that was talking more in general about adaptive systems. And actually, that book had a lot of wisdom in it, but people didn't, it was hard to understand. So only in the 80s, came out another book by David Goldberg, that was about genetic algorithms. And it made it very easy to understand it. It popularized it. And people actually started using it since then. But now, in hindsight, you can maybe go back to Holland's book, which is still available, and maybe see a much better and more mathematically rigorous picture of how these things work and what can be done with it. And it's possible that there are books about genetic algorithms, but they are probably more like, well, I've seen one book that was, I think, meant more for maybe younger people, but there could be others. I have not really read any of them, I have to say that. But I have to say that when it comes to it, you are in the same position as I am. We can go search and find what looks like a good resources. Anything else? Oh, Jyoti, I see you in the moderation. I would like to. I'll bring you up here if you want to talk. Does it work? It didn't work until now. I tried 3 times. Actually, it worked once. So, Jody, I'm trying to bring you up here to talk to me. Anybody else wants to join me on the video? We have like 10 minutes, so we can also. You're welcome to use the chat, but you're welcome also to join me here in the video, so I can see your face. Everybody can see your face, and we can talk. So I try to get Jyoti here. I know how he looks like. I've seen him before many times, but still be nice to see him. But it doesn't work. What's going on, Jyoti? Is it not working? Oh, okay. How about anybody else? How about Steven or Scott? Oh, any other questions by chat? Okay, here is Steven.
Hello.
Ah,
Hi.
Hi. Tell us about yourself. I'll take my glasses so I can see you better.
Okay, that's awesome.
So where are you from?
I'm Steven Makunja. I'm from South Africa, and I work as a full stack developer. I work for a company called PlaySafe Systems, and we are in the microgaming space.
What is that? What is microgaming?
Well, it has to do with online casino, online gambling. Yes, so we create we provide a platform for the online casinos, and also the content as well for those particular games.
Do you use machine learning at work, or is it more of a personal hobby?
Not yet. We are not yet using machine learning, though I think with these kind of discussions, it's something that's interesting to implement. So basically, mostly it's web-based applications using Spring Boot, and also some other architectural projects like Service Mesh and any other related systems around that. Yeah, but AI. Sorry.
Do you use serverless platforms or cloud platforms, or is it your own servers?
Yeah, we do use some of GCP, functionalities, and also a bit of our own. So it's just a mixture of both.
So what is your interest in machine learning? What do you like about it, or what do you do with it? What do you want to do with it?
I think I have an interest with human safety. So I think I would want to use it to create systems that can provide better awareness to people in terms of safety hazards, specifically when it comes to machines. You tend to find that sometimes we are not better informed when something has lived its time, or if a job is not, a maintenance job is not done properly on a particular machine, which might be a hazard to human life. So I feel I can use machine learning for towards human protection.
That's great. Actually, that's area that I haven't heard much about. So very good thinking.
Thank you. Yes.
So, have you seen other presentations today?
Yes, I have attended another presentation on the best principles for a Java developer, and it was also quite interesting discussion as well, with some of those things that as developers mostly sometimes you tend to just ignore, things like having good comments and things like the naming conventions, unit tests, and all those things. You just want to make the code work. So it was actually a quite informative discussion, and yeah, I really learned a lot. And also the previous presentation that you did as well. Yeah, I also learned a lot. So it's been quite an amazing experience, I think, since the lockdown started, having these online conferences. I would say it has been beneficial, because sometimes the conferences will be scheduled, but then maybe you don't have the finance to attend physically. But when it's online, yeah, it's really awesome.
You actually remind me that I also run a virtual AI group with presentations that have to do. It's called the Enterprise AI. So I'm going to give this link here in a second, if I find it.
Nice.
So this actually was designed to be a virtual user group. It was before the Corona started. Even we were a virtual user group. We try to do it in a time of day that is maybe more convenient to more people. So I don't know if for you it might be more. What is the time for you now?
Right now it's 3 minutes to 1.
1 a.m. right?
1 a.m. Yes.
Okay. So in this group we try to do things around 1 p.m. here. So which is like well, now it's 7 p.m. here, so it will be 6 hours earlier. So it will be more convenient for you, or it's supposed to sort of cover between maybe Hawaii and the Middle East or something like that. I think people like in Russia or in Japan, or in Australia, they probably will be. It will be not the greatest time for them, but for a lot of other people, it's okay. So we actually, and also in this user group, we have a video YouTube channel, so you can see all the previous presentations, and they just
awesome.
And there are many others. I mean, I like to talk about the stuff I do, but there are a lot of other resources and user groups and videos, and you can learn a lot. It's always nicer to be in a group and to interact.
Yeah, I'm actually seeing the benefits. Like I've always desired to attend conferences, but then, like I'm saying, due to the geographical limitations sometimes.